Welcome back. In the last lecture I discussed summer air conditioning system and the psychrometry of summer air conditioning systems. In this lecture I shall discuss evaporative air conditioning systems, for the winter and an all year air conditioning system. So the specific objectives of this particular lecture are to discuss evaporative air conditioning systems, winter air conditioning systems, and finally all year air conditioning systems. At the end of the lecture you should be able to explain the working principle, advantages, disadvantages and applications of evaporative air conditioning systems, explain the working principle of winter air conditioning systems, and describe all year air conditioning systems. So let me give a brief introduction to evaporative air conditioning systems. Conventional summer air conditioning systems, which we have discussed in the last class, which are capable of maintaining exactly the required conditions, are expensive to own and operate. By conventional air conditioning systems for summer, what I mean is the air conditioning systems which are based on refrigeration cycles, which in turn are based on either vapor compression systems or vapor absorption systems. These systems can be used in any location and they can be used for precise control of the space conditions. Okay. However, they are very expensive and they are expensive, not only the initial cost is high, but the running cost is also high. So, you will find that in certain applications the cost may be prohibitive. In such cases one has to look for alternative systems. Okay. So, evaporative air conditioning system is an alternative to summer air conditioning systems which can be used in hot and dry climates. So, evaporative air conditioning systems are inexpensive and they offer an attractive alternative to the conventional systems in hot and dry places. And evaporative systems also find applications in hot industrial environments where the use of conventional systems becomes prohibitively expensive because of the large loads involved. So, the evaporative cooling, the principle is very well known and it has been in use for many centuries for cooling water and for providing thermal comfort in hot and dry areas. All of us know that in hot and dry places you can cool water by storing it in earthen pots, and here the principle is that the water evaporates from the porous surface of the pot and as a result the water stored in the pot gets cooled. So, we all know this, and we are also familiar in hot and dry places that we use dry herbal mats called as khus, which provide us, when you wet them and when you expose it to an air stream, they provide us with cool and nice smelling air. Okay, so these principles are very well known and they have been in use for many centuries in many countries including India. Okay. So, what is the principle behind this? So, these systems are based on the principle that when unsaturated air comes in contact with a wetted surface whose temperature is higher than the dew point temperature of air, some water from the wetted surface evaporates. So, there is a basically evaporation of water from the wetted surface. As a result of this, the air which is in contact with the wetted surface becomes cool and humidified, and this cooled and humidified air can be used for providing thermal comfort. So, this is the principle, a simple principle behind the evaporative cooling systems. Now, evaporative cooling can be provided either by a direct process or using an indirect process or using a combination of both. First, let us look at the direct evaporative process. In direct evaporative cooling systems, the process or conditioned air comes in direct contact with the wetted surface and gets cooled and humidified. That is why you call it as direct evaporative system, but because there is a direct contact between the wetted surface and the process air. And in an ideal case, the exit temperature of air will be equal to the wet bulb temperature of the incoming air. I will explain what is an ideal case. However, in actual system we find that the exit temperature will be a few degrees higher than the wet bulb temperature of incoming air. So, let me show the schematic of a direct evaporative cooling system. So, here you can see a simple an elementary direct evaporative cooling system. This is called as a single stage system. You can see from the schematic that outdoor air, okay, outdoor air which is hot and dry, dry means which has very less moisture content, first flows through a filter. This filter filters the air and it removes any dust particles, etc., and the filtered air flows through an evaporative cooler or an air washer. In the evaporative cooler or the air washer, this dry and hot air comes in contact with a wetted surface or a water spray if you are using an air washer. Since this air is unsaturated, there will be evaporation of water from the wetted surface to the air. Since evaporation is an endothermic process, the latent heat of evaporation has to be supplied, and this latent heat of evaporation is supplied by air or water or both. So, in this process what happens? The air which comes out of the evaporative cooler becomes cooled. Okay, it loses its temperature because the sensible heat is used for converting water liquid into vapor. Okay, so at the exit of the evaporative cooler you have cool and moist air or cool and humidified air. Okay, cool and humidified air. So, this cooled and humidified air is blown into the conditioned space where you want to maintain the comfort conditions using a blower. Okay, so that air you call it as supply air. So, this supply air which is at a lower temperature but at a higher humidity flows through the conditioned space, and as it flows through the conditioned space it extracts the sensible and latent heat from the building, and it maintains the conditioned space at the required conditions, and finally the air is exhausted or vented out of the building. Okay, so this is the principle of an elementary direct evaporative cooling process system. The same thing is shown on the psychrometric chart here. We have the dry bulb temperature on the x axis and humidity ratio on the y axis. So, point O is the condition of the air at the inlet to the system. Okay, so as you can see here, the temperature is high and humidity is low. That means the air is hot and unsaturated. So, as it flows through the evaporative cooler or air washer, it gets cooled and humidified. So, its temperature reduces and its humidity increases. That means it follows the process OS. Okay, so it moves in this direction. And point S is the exit condition of the air at the evaporative cooler, and this air which is cooled and humidified is sent to the conditioned space. So, as it flows through the conditioned space, it extracts the sensible and latent heat and finally leaves the conditioned space at this state I. Okay, and this line SI is nothing but room sensible heat factor line, which we have discussed in the last lecture. Okay. So, this is the basic principle of direct evaporative cooling system. As I have mentioned, in an ideal case the exit temperature of air will be equal to the wet bulb temperature of the incoming air, but in an actual case the exit temperature will be higher. So, what do we mean by an ideal case? Ideal case means this evaporative cooler or the air washer is perfectly insulated. Okay, then you call it as this is perfectly insulated from the surroundings. Okay, that means the process is adiabatic, right, and there is an infinite area of contact between the air and the wetted surface. Okay, in such cases what happens is the process line follows the constant wet bulb temperature line. So, if it is perfectly insulated, this is your constant wet bulb temperature line. Okay, and the exit condition will be same as the wet bulb temperature, that means the exit will lie somewhere here. Okay, so this will be our exit temperature, right, in an ideal case, but you will find that in an actual case there will be some heat leaks into the system. As a result, the process line lies slightly above the wet bulb temperature line, and the exit temperature will be higher than the wet bulb temperature. That means instead of being here, the exit condition will be at point S, which is few degrees higher than the wet bulb temperature line. Okay. Since the exit temperature is higher than the wet bulb temperature line, we can define what is known as saturation efficiency or effectiveness of the evaporative cooling system, epsilon. This is defined as you can see here, T naught minus Ts divided by T naught minus T naught subscript WBT, where T naught is the inlet dry bulb temperature, Ts is the exit dry bulb temperature of the air, and T subscript OWBT is the wet bulb temperature at the inlet condition. So, this is very clear from your psychrometric chart. If you look at the psychrometric chart, this is the expression for effectiveness or efficiency. As you can see, T naught minus Ts is nothing but this temperature drop. Okay, or you can call this as actual temperature drop, and T naught minus TWBT is nothing but this. Okay. So, in an ideal case you get this, but in an actual case the actual temperature drop will be lower. So, the efficiency or effectiveness is nothing but this divided by this. Okay. So, depending upon the design aspects of the evaporative cooling system, the effectiveness may vary from 50% for simple drip type evaporative coolers, and it can be as high as 90% for efficient spray pads or air washer based systems. Okay, so the efficiency will vary from 50 to 90% depending upon the design. Now, the required flow rate of air is obtained from energy balance of the conditioned space. We have to find out what is the required air flow rate. So, that can be easily obtained if you take a control volume across the conditioned space, and if you assume that steady state conditions prevail. So, you take a control volume across this and apply energy balance, okay, and neglect kinetic and potential energy changes. So, the rate at which heat is being added to the conditioned space, that is nothing but QT, should be equal to the rate at which heat is being extracted by this air stream. Okay. So, energy balance becomes QT is simply equal to m dot S into Hi minus Hs, where Hi is the exit enthalpy, Hs is the inlet enthalpy. Okay. So, this is the energy balance, assuming of course negligible kinetic and potential energy changes for the supply air. So, from this expression you can find out what is the required air flow rate m dot S, which is nothing but Qt divided by Hi minus Hs. So, if you know what is the rate of heat transfer to the conditioned space Qt, if this is known, and Hi is nothing but the enthalpy of the conditioned space air, so which is normally known from our requirements. So, Hi is known to us, and if you can fix the supply condition Hs, then you can find out the required mass flow rate of supply air. Okay. Compared to the conventional refrigeration based air conditioning systems, the air flow rate required is much larger in case of evaporative cooling systems. This can be viewed as an advantage, or it can also be viewed as a disadvantage. Normally it is observed that for the same cooling capacity and for the same inlet and outdoor conditions, the required air flow rate in case of evaporative air cooling systems will be about 8 to 10 times. It can be as high as 8 to 10 times that of a normal air conditioning system, which is based on vapor compression or vapor absorption system. So, the air flow rate required is very high. Okay. And the required air flow rate increases as moisture content of outdoor air increases. This I will explain with the help of a psychrometric chart. And we also find that beyond a certain moisture content value, evaporative cooler cannot provide comfort as the cooling and humidification line lies above the conditioned space condition. Okay. So, one thing you must observe is the required mass flow rate increases as the outdoor air humidity increases, and beyond a certain point these coolers will simply they cannot simply work. Okay. You cannot use the coolers when the outdoor air humidity exceeds certain value. Okay. So, let me show that by using a psychrometric chart. Okay. So, this is again what I have shown earlier. This is a psychrometric chart. You have the dry bulb temperature and humidity ratio, and this is your cooling and humidification process that take place in a evaporative cooler. Okay. So, O is the inlet condition and S is the supply condition, and we have seen that from energy balance the required air flow rate m dot S is Qt divided by Hi minus Hs. Okay. Let us say that this is your humidity, that means this is your inlet condition, okay, which is nothing but the condition of the outdoor air. Then Hi minus Hs is nothing but, if you draw an enthalpy constant enthalpy line, this is your Hi minus Hs. So, you can see that the required mass flow rate is inversely proportional to this enthalpy difference. Now, if the temperature remains same, let us say, and the humidity ratio increases to this point. Okay, when the humidity ratio increases to this point, Hi minus Hs decreases, because now the Hi minus Hs is this. Okay, since Hi minus Hs decreases, mass flow rate of air increases. If the humidity increases further to this point, let us say, then there is further reduction in enthalpy rise across the conditioned space. So, there is a further increase in the mass flow rate of conditioned mass flow rate of the supply air, and you find that beyond a certain point, for example, if you let us say that humidity ratio is at this point, temperature is same but humidity ratio is here, then when you use an evaporative cooler, you find that the process line proceeds like this. Okay, that means it does not intersect this room sensible heat factor line at all. Okay, that means you cannot use evaporative cooler beyond a certain point. In fact, when the humidity ratio lies at this point, and if the process line passes through the conditions point I, then you will find that the required amount of supply air is infinite. Okay, so, beyond a certain humidity ratio, this system does not work. Okay. So, this is a very important thing one must keep in mind. Now let us look at indirect evaporative cooling system. So far we have discussed direct evaporative cooling system. Now let us look at indirect systems. In an indirect system, we use a primary air stream and a secondary air stream. That means two air streams are used. The primary air stream becomes cooled and humidified by direct evaporation process, whereas the secondary air stream, which is nothing but the supply air to the conditioned space, undergoes only sensible cooling as it exchanges sensible heat with a cooled and humidified air stream. Though the temperature drop of secondary air is lower compared to a direct process, since the humidity ratio remains constant, the indirect systems may be applied over a broader range of outdoor conditions. Okay, this is the advantage of indirect evaporative cooling systems over direct evaporative cooling system. Now let me show a schematic of indirect system. Okay, so as I said, here you have two air streams, one is primary air, the other one is secondary air. Okay, so first primary air is cooled and humidified in this evaporative cooler. So this is your evaporative cooler. Okay, so as the primary air flows through this evaporative cooler, it gets cooled and humidified. Now this cooled and humidified air is blown through an air to air heat exchanger. Okay, so this is an air to air heat exchanger. Let us for the sake of simplicity, let us assume that it is a fin and tube type of heat exchanger, and this cooled and humidified air flows through the tubes, let us say. And the secondary air, which is nothing but the supply air to the conditioned space, flows over the tubes and over the fins. Okay, so there is no direct contact between the primary and secondary air. Okay, so secondary air is flowing in this direction and primary air is flowing through the tubes. Since the temperature of the primary air is lower than the secondary air, there will be sensible heat exchange between the secondary air and primary air. As a result, you find that the secondary air gets cooled sensibly. Okay, so at this point the temperature, let us say this T outlet will be lower than the T inlet for the secondary stream. So this cold air is supplied to the conditioned space for providing thermal comfort. Okay, so this is the this is an elementary indirect evaporative cooling system, and the same thing is shown here on a psychrometric chart. You can see here that process O to O dash is what happens to the primary air as it flows through the evaporative cooler. As you know, it gets cooled and humidified. In an ideal case, it leaves the evaporative cooler at the wet bulb temperature. Okay, so this is the process undergone by primary air. So at this point, this air enters into the air to air heat exchanger. Okay, so in the air to air heat exchanger, this exchanges heat with the secondary air, which is again at this temperature. Okay, so there is heat exchange between the hot air, which is at this temperature, and cold air, which is at this temperature. Okay, so since there is no direct contact, the secondary air undergoes only sensible cooling, so its temperature reduces in this direction, and the primary air temperature increases in this direction. Okay, so finally the primary air is exhausted at this point at condition E, and the secondary air, which is at the temperature S, is supplied to the conditioned space. You can see here that the secondary air, which is nothing but our conditioned air, gets cooled, but its humidity ratio remains constant. Okay, that means inlet and outlet humidity ratios remain constant. So this is an advantage of indirect cooler, because we are not increasing the humidity of the air. Whereas you can see that the temperature drop of the secondary air is only this much. Okay, whereas the temperature drop of the primary air is higher. Okay, so this is one disadvantage of indirect evaporative cooler, because the available temperature drop is reduced. In modern day, what I have shown is only a schematic, and in modern day indirect evaporative coolers, what is done is the conditioned air flows through tubes or plates made of non-corroding plastic materials such as polystyrene, PS, or polyvinyl chloride. Okay, that means what happens in an modern indirect coolers are, you have a tube, let us say. Okay, you have a tube like this. Okay, this is just a schematic. So through this your secondary air flows. Okay, secondary air. Okay, so this is the wall of the tube, and you maintain a thin layer of water on the outside of this tube. So this is a layer of water. Okay, so this is a water layer, and over this the primary air will be blowing. Okay, so as the primary air blows over the tube, the wetted tube, water evaporates from the thin layer. Okay, so as a result, there is a sensible heat transfer here. So this layer becomes cold, and there will be heat exchange from the thin layer to the secondary air, which is flowing through the tube. Okay. So, as I said, on the outside of the plastic tubes or plates, thin film of water is maintained. Water from the liquid film on the outside of the tubes or plates evaporates into the air, blowing over it, and cools the conditioned air flowing through the tubes or plates.